Okay, so now problem 3, part 2. Consider a still sphere of mass m colliding elastically head-on at speed u with a stationary identical still sphere. So here we have an object with mass m moving at speed u, and this object is at rest. They are identical, so they both have the same mass m, and they will collide at some point. And this object will have a velocity 1, and this object will have a velocity 2. Because of the problem, I still don't know what will happen to the velocities here. That is something that I will find better, but I know that they will collide. And I also know, important, that this is an elastic collision. Because this is an elastic collision, I know that energy is conserved. But I also know that these objects will not stick together. You see, when two objects collide inelastically, they stick together. But because this is not an inelastic collision, but an elastic one, I know for sure that they will not be stick together. So there will, after the collision, the mass will not be the sum of both masses. Something like 2m. I see some of you did this in the solution, so that is wrong. The mass after the collision will not be 2m, okay? Because this is elastic. That happens in elastic collisions, and this is not the case. Alright? So, for letter A, use conservation of linear momentum to write a general expression for the total momentum before and after the collision. So, momentum before is mass of the sphere multiplied by initial velocity plus 0. So this one is coming from this because it's moving, and this 0 is coming from this because it is at rest, and because it's at rest it has no momentum. And what is the momentum after the collision? So the momentum because of this one is the mass by its velocity plus the mass of this one by its velocity. You see here, I have two different velocities because I don't know what will happen. One of them may stop and get to 0 or something else. At this moment of time, it's not sure yet. Now, using conservation of linear momentum, I have that mu is the same as mv1 plus mv2. Okay? From here, I can cancel m and get this. Okay, so the answer is this one, but this will be helpful for letter C. Alright, and let us call this A. Now for letter B, kinetic energy is before 1/2 of the mass by the velocity square. The second one doesn't have kinetic energy because it is not moving. And what is the kinetic energy? After 1/2 of the mass by v1 square plus 1/2 of the mass plus v2 square. Okay, so now if we equal both equations, I will get 1/2 of the mass u square equals 1/2 of the mass v1 square plus 1/2 of the mass v2 square. Okay, so that is answer to letter B. And also from here I can get another equation. If I cancel out common terms, I will get u square is the same as v1 square plus v2 square. You see? And this is the equation. Let's call this B, equation B. we are gonna use both A and B for letter C. In letter C, we have to show that the initial stationary sphere, this one, no, this one, this is the initially stationary, will be moving at velocity u, and this one will stop. Okay, so that is what I want to prove. That is something that I don't know yet. So it is wrong if you use the fact that v1 is 0 for proving, because that is something you don't know. So if you use what you want to prove as the procedure for your proof, that is wrong. So I see some of you took the assumption that v1 is 0, so you just took something like 1/2 of mass v2 squared equals 1/2 mass times 0, and something like this. You cannot use this fact, because that is something that you don't know yet. That is what you are trying to prove. That is wrong. So the way to prove this is by using these two equations that we get from letter A and letter E. That is something that is okay, because you know that from the previous letters, and you are not taking any assumption here. So you got this from momentum conservation, and you got this from kinetic energy conservation. We got this from two different formulas. So if I plug in A into B, what will happen? It will happen, I will get B1 plus B2 squared is the same as B1 squared plus B2 squared. You see? All I did here was take this and place it here. Okay? I can do that because they both relate U. Now from this equality, I have to solve for the left side. If I develop that square, that will be b1 squared plus 2 times b1 b2 plus b2 squared, and that has to be the same as v1 squared. So this has to happen in order to meet both equations. So from here I can cancel this with this and this with this, and that is 2 times b1 b2 equals 0. And from here I know that b1 b2 is 0, and here are two possibilities. Okay, that either b1 is 0 or b2 is 0. Okay, remember here the diagram. v1 is the final velocity of the first object, and v2 is the final velocity of the second object. Okay, so from A, if the velocity of the first object final is 0, then u, second velocity, has to be u. Okay, and same here. So here are two possibilities. And the one that I'm going to take is this one. That the first object final velocity is 0, so it stops, and the second one takes velocity u. Why? Because this would not make sense. Because it would suggest that after colliding, the second one kept at rest, and the first one passed through the first one and kept moving at the same speed. You see? That is not a possible scenario. What could happen is that it bounces back. But if it bounces back, then I would have gotten something like negative u here. But that is not the case. So what this answer is suggesting is that the second object stayed the same while the first one continued moving to the right side. Which of course is not possible because this ball cannot pass this without bouncing back or sticking or something. That is not a possible scenario. That could never happen. Not possible. However, this one is totally possible. And this one suggests that the final velocity of the first object is 0, so it stops. And the final velocity of the second one is now u, which is the way to prove that the initially zero sphere moves off at speed u and the initially moving sphere stops.